All right, so today we are going to go over, let me just quickly put up the agenda here. We're going to quickly go over isomers. And then if we have time, I will also be going over chairs and then Newman Projections and Fischer Projections. Have you guys started looking at Newman and Fischer Projections yet? Yes, all right, perfect. Okay, so with that being said, let me quickly go over isomers, okay? So isomers, hopefully you guys have covered chirality by now. And when I mean chirality, I'm talking about RNS. Just a reminder. R is clockwise. S is counterclockwise. Okay? And if you guys don't know what I'm talking about, this is chirality. When they ask you what is the chirality of this chiral carbon, they are asking you to write either R and S. And to figure out R and S, you have to rank your 4 groups by priority, and the priority is weight. The biggest one is number 1, the smallest atomic mass or weight is number 4. And then you have to look at if the 4th group is on a wedge, dash, or a line, and depending on that, you keep, flip, or rotate. All of that is on last week's weekly review, all of which is on our YouTube channel, Peer Tutoring at UT Dallas. So all previous weekly reviews are on there in a playlist for this semester. There are also previous semesters like spring, if you guys want to check them out too. All right, so hopefully you guys are all on the same page now. So in RNS, there are 2 specific ones. One is called enantiomer, and the other one is called a diastereomer. Okay. Enantiomer is also called a mirror image, which is exactly what it sounds like. When you have 2 structures and you put them right next to each other, they should form a mirror image of one another. Okay. And then another side note is all chiral carbons must flip. Okay. Whereas diastereomer, at least one chiral carbon must flip. Okay. So for example, when I have, let's say, structure 1 and structure 2. Okay. The first step is you're always going to find your chiral carbons if it's not already labeled out for you. And after that, you're going to find R and S. Okay. Let's say, for instance, after you've done all that, you get, actually, let me type this out. You get R, R, R. And then for the second structure, in order for this to be an enantiomer, what should it be? Give me all 3. Any guesses? Yeah, someone got it. So yeah, a couple people got it, so it should be S, S, S. So like I said, all chiral carbons, sorry, let me fix that. All chiral carbons must flip, okay? And flipping means R to S or S to R. So if my first structure is, once I find chirality for my first structure and I get all R's, my second structure has to be all S's in order for this pair of structures or isomers to be called an enantiomer. Now for diastereomer, structure 1, structure 2, let's say I get, once again, R, R, R. What is one possible combination for my structure 2? That's correct. It could be R, R, S. It could be R, S, S. Correct. It could be S, R, R. It could be S, R, S. As long as it's not S, 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 and you know there's probably more combinations like S, S, R, and then I think that should be it. Maybe R, S, R. I think there's only 6 combinations, but any of those 6 will do. You don't necessarily have to say all of them. Just when you do it, as long as one of these positions are flipped, one or more is fine, as long as it's not all 3. So if there's 3 chiral carbons, the max you can flip is 2, and the minimum being 1, obviously. Okay, so any questions on enantiomer and diastereomer? All right, perfect. So if you got that, that honestly should have been the hardest part of isomers. So hopefully the rest of these will be easy. So the next one is called cis/trans. I don't think that's the exact name for it, but sometimes it's called geometric. But geometric or stereoisomers can mean cis and trans. Sometimes it could also mean one of these, because these are technically stereoisomers also. They're flipping, and yeah. So I just like to call it cis and trans. For cis and trans, hopefully this should be a review from Gen Chem. But if not, I'll quickly go over it. So first we're going to deal with double bonds. So let's say you have a double bond right here. And let's say you have, so in order to see if this is cis or trans, you split it down the middle. And then, so you have a left side and a right side. Between the left side, or in one side, you have to see, you have a top and bottom. Okay, you have to see between these two, which one is heaviest. Okay, whichever one is heavier, you put a for it, and the smaller one or lighter one, you put a B. And then you do the same for the right side. And let's say the A is also on top and the B is on bottom. So if we have this, you have to look at the direction your A's are pointing towards. Okay, they're both pointing up. So would this be a cis or a trans molecule? Okay, yeah, so it's cis. So this is just the easy part. Okay, so same thing for trans, but this time we get opposite direction. So let's say when we split it in the middle, we look at the weight, and then we get actually A on the opposite side. This would be trans. Okay, so double bonds are one way to figure out cis and trans. Another way to figure it out is wedges and dashes. So if it's cis, cis, by the way, hold on, equals same direction, and trans equals opposite direction. Okay, so I'm sure you guys are good with that, but something that might be new or different are wedges and dashes. So let's say in order for to show cis through wedges and dashes, you have to have two points where you have two wedges, or both dashes. Okay. Remember, wedges means facing up or towards you, and dashes mean facing down or away from you. Okay. Also, going into the page or out of the page. Let me also write those down. Out of the page, into the page. Okay. That's just simple wedges and dashes, not cis or trans. But for trans, of course, you're going to have one of each. One wedge, one dash. Okay. All right. So that should be straightforward. Let me know if you have any questions. The next one is called constitutional, also known as structural. Okay, and I like to use the word structural more because it clicks better. Structural has the word structure in it, and that helps me understand. So let's say we have a formula of C5H12. Okay, so if I have C5H12, I should have, in order for this pair, I should have two different ways to arrange this. Okay, kind of like a puzzle piece. Okay? So one way is to draw it like this. So just straight 5 carbons. Another way is to draw 4 carbons and place the 5th carbon right there as like a methyl. Okay. So this would be 1, 2, 3, 4, 5. Well, there's no name for it, but this is like pentane, and this is kind of like isopentane. Well, not really, but you get the idea. So structural means they have the same formula, but they look different. Okay, from a visual aspect, they look different. So basically, all I did is move one of the final methyl groups onto this carbon right here. Okay, hopefully that should be straightforward too. Next up, we have resonance. They don't always use this, but sometimes you might see it, so I'm just covering my bases. Okay, so resonance should be simple. Obviously, it's going to be a little bit more complex than this, but let's say your first structure looks like this, with the positive charge there, and then your next structure looks like this. If it has any type of charge and you see the charge move, most likely it's a resonance, but obviously double check. Okay. And then, sorry, I'm kind of running out of room, but another RNS topic that I kind of forgot, or I didn't forget, but it kind of relates to the same idea, is something called not related. Well, it's not like a legal term, but those two structures are not related. They're not similar. They're not anything. And you can figure this out by looking at the chirality, okay? So not related also means that basically they have different formula, okay? So for example, let's say you have a bromine, a hydrogen, a methyl group, and a chlorine. And then let's say you have the same thing, but bromine, hydrogen, methyl, and instead of a chlorine, you have a fluorine, okay? If you see these two structures and you see chlorine on one structure and fluorine on the other, that is a different chemical formula, and the answer choice would be not related, okay? It's not an enantiomer, it's not a diastereomer, it's not any of these. And sorry, technically, my mistake. Technically, it doesn't relate to RNS, but sometimes, actually, yeah, regardless if you get both R's or RS, it won't matter. But what does matter is something called, last but not least, it's called identical, also known as same structure, or just same. So let's say your first one and second one. Let's say you get R, and your second one you get S. Okay. So it has to have same molecular formula and same chirality. Okay. So sometimes these two can get a little bit mixed up. So make sure you guys don't mess that up. Usually identical will have some type of chirality that you can like identify. And constitutional it's pretty obvious when it's like structural. Okay, so any questions on any of these? That should be all the isomers you guys should know. If there's anything else that I haven't covered or missed, or you guys want me to explain a little bit more, let me know. Okay. All right. So I'm just gonna wait a few more seconds before I clear the page. So if you're still taking notes, let me know. I can keep waiting or take a screenshot. And you don't never really have to be in a hurry to take notes because everything will be posted on a recording. But if you want it right then and there, then the best advice I can say is to just take a screenshot. Okay, so if no one has any objections, I'm gonna clear the board and move on. Just a little side note, for OCHEM, for peer tutoring, we do have a exam review. So before every exam, you guys will have a exam review, and obviously you still have your weekly reviews every single week at this time. But for your exam review, it's actually this Saturday, September 19th, from 10 a.m. to 1 p.m. And you can find that probably on like a little tab, just like how you found this workshop or weekly review. So it should be, in virtual rooms, and then there'll be a little tab for exam reviews. Okay. So that, once again, that's this Saturday from 10 a.m. to 1 p.m. So the first 2 hours are kind of going to be like a lesson of some sort, and the last 2 hours are going to be like kind of like Q&A. Okay. I believe there is a cap, so you might want to be on time or early. Okay. All right. So I'm going to clear the board. So I will. There is one more lesson before the exam. Your exam is on next Wednesday, and then I also have next Tuesday for review, to cover chapter 4. Today we're going to finish up chapter 5. I don't think we should get started until next week for chapter 4, because it's, like I said, completely different. So I want to answer all your questions regarding chapter 1, 2, 3, and 5. All right, so in chapter 5, we covered chairs, Newman projections, and Fischer projections. I know you guys haven't covered Newman and Fischer yet. I believe they'll cover it this week, if not already. If not, I believe they should. So I'm just going to quickly cover it just in case. So I'm going to go over Newman and Fischer actually right now, and then chairs we can I'll let you guys ask me questions on it. So give me 1 second to put everything on the board, and I'll talk. And just to confirm, you guys haven't covered Newman or Fischer projections, correct? Oh, you guys have. Okay, perfect. Was that today? So, okay, what I'm doing is... Okay, all right. But what about in lecture? Has anyone covered it in lecture? Okay, all right, cool. All right, so then this would be a lot easier. Okay, so the question is going to ask, it's going to give you a line angle, and you have to either convert it to a Newman or to a Fischer, or they might give you the Newman projection, they'll ask you to convert it to a Fischer, and vice versa. Okay, so you have to be comfortable going from either form to another form. Okay, so we're going to start with line angle. So this is our line angle, and there is a wedge here. And then let me know in the chat, out of chair, Newman, and Fischer, which one is the most difficult one? Newman. Okay, I got 2 Newmans. All right, so 3 Newmans. All right, Newman actually it's not too bad. I honestly think chairs are sometimes the hardest, at least when I first started. Okay, I got 1 Fischer. Okay. Actually, yeah, I agree. Fischer is probably the hardest. They're all relatively on the same level. But anyways, so here is the problem, and then sometimes, or most of the time, they should tell you which way you're looking at from, okay? And they'll give you some kind of like eyeball, or you might have to draw it, or maybe Dr. Pan or one of the other professors drew this in their lecture notes. So let's say you're looking from left to right from this angle, okay? And then they'll tell you carbons 2 and 3. You know, this is our compound, and they'll tell you that that carbon 2 is in the front, okay? What that means is, first of all, when we draw our Newman projections, we're going to draw one big circle. This is considered your back carbon, which in this case is carbon 3. And then I'm going to draw a dot, which is carbon 2, okay? So I am going to draw it like this. Oh, let me erase that. Okay. So you have to make 2 Y's. Okay. So keep in mind this is one way to draw it. The other way to draw it is where everything is flipped, where the Y in the front is facing downward and the Y in the back is facing upward. Okay. And I drew it in this particular direction because my line, my methyl is facing downward for my bottom, or for my front carbon, and my line methyl in the back carbon is facing up. Okay. So I'm going to use this example. So these are lines. These are either wedges and dashes. Wedges and dashes. Okay. Now, it has to be, you have to figure out which side is wedges and which side is dashes, left or right. And each, depending on which way you're looking at, it will matter, okay? And both wedges will be on one side and both dashes will be on the other side, okay? So if you're looking from left to right, which is what we're doing right now, we're looking from the left side to the right side, then your dashes will also be on the left side, okay? And this is kind of something I remembered. I'm sure visually that's why this lesson might be a little bit hard, because you can, you know, some people like to use the model kits or like maybe a YouTube video to perfectly see it, or in person rather. But what I found is if wherever the eye is from, that's kind of the side your dashes go. So if you're looking from left to right, your dashes will also be on the left side and your wedges will be on the right side. But let's say you're looking from right to left, then your dashes will be on the right side and your wedges will be on the left side. Okay, so in this example, our dashes will go on the left side. So I'll write that down. So all of our substituents that are on dashes will go bond there, and of all of our substituents that are wedges will bond on the right side. Okay. Now the easiest ones to fill is obviously our lines. Lines mean they are on the plane. So both of them looks like they're just methyl groups. So I would just put a CH3 here and a CH3 here. Sorry.
I didn't get.
My bad. So CH3. 3? Okay. Is anyone confused where I got CH3 from, or anything so far? Hopefully, I know the dashes and wedges are a little bit confusing, but hopefully I explained it properly. Okay. So we're going to continue. Oh, I don't know why there's an echo. All right, so yeah, so someone asked, can I repeat how I got dashes on the left and wedges on the right? So it all depends which direction you're looking at, okay? So in this particular problem that I made up, it tells us that the left side is what we're looking at. Carbon 2 is the front carbon, okay? So this is the front carbon. So, I mean, this is kind of something that I kind of memorized. I'm sure if you have a model kit or have someone explain it to you in person um, with like pencils or pens, you can kind of see it. But this is kind of how I denote it, and it kind of works. And yeah, so once again, wherever the eye is, or whichever side you're looking from, either left to right or right to left, wherever that's starting from, that's where your dashes start from, okay? And then obviously the other side would be wedges. There's like lots of ways to solve it. This is kind of how I solve it. So, all right. So moving on, filling in all of our stuff. I'm gonna start with the front carbon, which is this one and this one. So the front carbon, I have a butyl for on a wedge, and I have a dash methyl. So I have a methyl there. I have a terp butyl here. And I'm just gonna write T butyl. Okay, so someone asked, so if the I was on the right, then the dash would be on the right side of the Newman projection. Yes, that's exactly what I'm saying. And then another person said, so if the 3 had been the front, then we would have dashes on the right. Yes, that's also correct. Okay, so T-butyl there. Now for our back carbons, I have a ethyl here on a wedge, so here, and then a methyl again also on a dash. So CH3, and I'll just write ethyl. By the way, if they ever write Me, that means methyl. If they say ET, that means ethyl. Okay. Sometimes they abbreviate it, or yeah. Okay, so we're done. That's our Newman projection. Does anyone have any questions on this specific example? I'll kind of go over like the different types of Newman projections, like anti, staggered, and gauche. But for now, anyone have any questions? Okay, and then yeah, someone said, where is the T butyl on the line angle? The terp butyl is right here. So it's kind of hard to tell because of the wedge and dashes, but it's this one right here. So we have a carbon bonded to another carbon, which is bonded to 3 carbons. So let's say if I were to draw the line angle without any stereo chemistry, it would look like this. Okay, and this is our T butyl. Does that kind of help? And sometimes if you notice, this is actually not the longest parent chain or carbon chain, but that's okay. Don't bring in like nomenclature rules into this because it won't make sense. They will already kind of tell you which ones are on the line. Yeah, just focus on whichever one is on the line. That's the one you put right here. Okay. And then dashes and wedges, that depends on where the eye is. As if you're unsure, at the very least, just put dashes all on the same side, whether it's right or left, and put wedges on the same side. Okay, that will at least help you. I don't know. I mean, there's no partial credit because it's, multiple choice, but at least that's what I think. There's no multiple choice, or there's no partial credit, right? Or free response on the exam. Okay. What about the quiz that you guys took? It was all multiple choice, correct? Okay. Yeah, I believe the exam should also be all multiple choice. It's kind of hard to do, just especially because there's honor lock. It's kind of hard to do free response, like them asking you to print it out and then scan it back. Okay. Well, the free response, was that like fill in the blanks? It wasn't like, okay, yeah, that's, yeah. Yeah, Nomac is kind of like old school. So anyways. Okay, so any questions on how we got line to Newman? Because when we go to Fischer, that's when it kind of gets a little bit confusing. Oh, shoot, okay, hold on. I mean, I don't think so. They should all be the same format. Okay, also, my bad, I meant to put an H here. That shouldn't change anything. All that means is this one here is just an H. Okay. So after we do this, sometimes they will ask chiral carbons or chirality, and for Fischer we have to know chirality. Okay. Oh, sorry. So Fischer mean chirality. Okay. And if you notice, carbon 2 and carbon 3 are chiral, and almost always they will be chiral. Oh, sorry. This should also be a chlorine, not methyl. My bad. Yeah. That should fix our problem. All right, so we are going to find chirality of 2 and 3. So take a few minutes while you guys figure out chirality for carbon 2 and carbon 3. Tell me if it's R and S. In the meantime, I'll draw the Fischer structure. And then whenever you have the answer, please type it in the chat. All right, so anyone have any answers? This one is a little bit hard. At least carbon 3 is slightly hard. Okay, that's fine. I'll go over the answers. So I am going to put, or I'm going to label for carbon 2 by priority. So this group is number 1, this group is number 2, this group is 3, and that's 4. So if you see the direction, it should be counterclockwise. So carbon 2 is S. Now carbon 3 is kind of tricky. I'll write this in orange. So chlorine is number 1. This group is number 2. This group is number 3, and this group is number 4. Okay, I am labeling by weight. That weight takes priority, so whichever is heaviest takes priority. Okay, so let me explain my purple. So this is number 1 because this carbon is bonded to a carbon right here, a carbon right there, and a carbon right there, and a hydrogen. Okay, between 3 carbons and hydrogen, hydrogen is obviously number 4. Okay, so hopefully there's no questions regarding that. Now between 1, 2, and 3, I have to figure out after this first bonding of carbon, what is the next highest atom bonded to those 3 carbons? So the next highest atom bonded to this carbon is a chlorine, and chlorine is pretty heavy compared to hydrogen, which is bonded right here, and compared to another carbon, which is bonded right here. Okay, so between chlorine, carbon, and hydrogen, that's how I got my 1, 2, and 3. Okay. Did everyone understand that? Because that's very important in figuring out chirality, because it's not always easy to tell. You have to go more than a single atom. Okay. All right, so hopefully you guys understood that. So for carbon 3, my orange ranking, I have chlorine, obviously, it's directly bonded, that's the biggest. And then I have a carbon, okay, but this carbon is bonded to 2 other carbons, while this carbon is only bonded to a single carbon. Okay, so carbon with 2 other carbons takes priority, which is number 2, and this is 3, and then obviously just a single carbon is number 4, okay? As a result, the direction is also S. However, our fourth priority group is on a line, okay? And if you guys remember from last week's lesson, which I'll quickly go over, so a wedge, a dash, and a line. So if your fourth group is on a wedge, you flip your chirality. If it's on a dash, you keep your chirality, and if it's on a line, you rotate everything. Okay, you rotate so it's on either a dash or a wedge. Okay, and the reason why we do this is because you want your fourth group inside or into the page, your smallest group into the page. And if you ask me why that is, I think it has to do with steric hindrance, but you don't have to worry about the why of it. So the hard part is how to actually rotate this group, okay? And I believe I showed that last week too, but I can quickly go over. So I said that you keep all of your stereochemistry, which is where the lines and wedges and dashes are, and you have to rotate your fourth group to either a dash or a wedge, okay? And you can rotate as many times as you want, but it's simple just to rotate once. So I'm going to rotate to my dash. So my methyl is going to be right here. So CH3. My chlorine is actually going to be on a wedge. My ethyl is going to be on a line, and my R group, all of that is also going to be on a line. Okay. Now, once again, if we do priority, I should get 1, 2, 3. I got S. Sorry, hold on. Oh, my bad. Sorry, okay. You're not rotating everything. Something is going to stay, and that something is going to be your R group. So your R group is still right here, and your ethyl is actually right here, okay? And when you think about it, it's kind of hard to explain. Sorry, let me get rid of these. Okay. So my R group is right there. This is number 2, and this is number 3. So it's actually R. Okay. So carbon 3 is actually R, and my 4th group is on a dash, so we keep it. My 4th group here is also on a dash, so we keep both. And the reason why I only rotated these 3 is think of my R group as like an arm, and think of these as like 3 pencils I'm holding, and I'm like rotating all of these pencils, different kinds of pencils. So when I rotate, I have to keep one of these the same. And in this case, I chose the R group. Yeah, usually you just keep the biggest side, like the whole R group, and then you flip the tinier ones. Okay. All right. Hopefully that made sense. So all of this, what we're doing is to figure out chirality for S and R, because that determines which direction we place our groups on the Fischer projection. Okay. So before we go on to our actual Fischer projection, any questions on anything I've done so far? Okay. So if there's no questions, I'm gonna head into it. Okay. So on our Fischer projections, the lines, or in the middle, again, they are our lines. Okay, just like Newman projections. So, however, this is going to be like the top. So, okay, let me label this. Okay, so this is carbon 2, and this is carbon 3. Okay. Let me move this. Okay. So, with that in mind, there is a CH3 here and a CH3 here. Okay, just like how it was for Newman projection. Okay, so we just were looking from this. Okay, now we have to figure out chirality. Well, actually, we already figured out chirality, but we won't know for sure which way to put until we randomly place it, do chirality, and then flip it. And I'll tell you guys what I mean. Okay, so for example, for carbon 2, I'm going to place my hydrogen here, my T butyl here. I'm going to place my chlorine here, my ethyl here. Okay, so I just randomly placed it because I don't know for sure which direction it is until I do my priority again. Okay, which is exactly what I'm going to do right now. So I'm going to start off with my carbon 2 in purple. So everything in the group order should be the same. So the R group, sorry, R group was number 1, terbutyl was number 2, methyl was 3, hydrogen was 4. Okay, so this gives me S, or this gives me R, right? And I want S. However, you guys said you guys didn't do Fischer projections, right? In class yet? Or have you guys done it? Okay. So, okay, yeah, that's why this might be a little bit new. So, in Fischer projections, everything on the side are technically wedges. Okay. And because of that, we always have to flip whatever chirality we get. So when I placed hydrogen here and T-butyl here, I get a R formation, okay? Once I do that, and I have to automatically flip it because my fourth group will always be on the side. And because my fourth group is on a wedge, I have to flip it, remember? So fourth group, it's on a wedge, I have to flip it, okay? So because of that, we are going to put hydrogen here. Oh, sorry. And P-butyl here, okay? And it just so happens to work out perfectly because we do want it to be S, okay? Now when you do priority, you would get S, and that's exactly what we want. So this carbon 2 is good to go, okay? Now let's check carbon 3 in orange, okay? So once again, chlorine's number 1, R group number 2, ethyl 3, methyl 4, okay? So I want R. When I do the order, I get S, and then I automatically know, or sorry, yeah. So wait, hold on. Okay, my bad. For this part, we actually, when I mean flip, I don't actually mean you flip these. I mean like it naturally becomes R to S because these are on wedges. You don't actually have to flip these. Okay, so the H should actually be here. But for carbon 3, we get S, but we want R, correct? Hold on. So 1, 2, 3. So chlorine should be on here and ethyl should be here. Okay. So 1, 2, 3. So that's R. And then we flip it to get S. Actually, no. Yeah, we did it. Chlorine should be here. Okay. All right, so yeah, so sorry, ignore the last 30 seconds. So like I said, whenever we do chirality for this carbon, chlorine's number 1, R group number 2, ethyl 3. So if we do the arrows, we get S, but we have to flip automatically because of the wedges. So we get R. We don't actually have to flip. We don't actually flip it. The only time you flip it is if you actually do get R on the first try for carbon 3 and you want S, or sorry, if you actually do get R on the first try and you want R, then you have to flip it because it's already going to flip automatically. Does that kind of make sense? I know I kind of butchered that a little bit, but Fischer's kind of hard to explain. So let me check this. So 1, 2, 3. Okay. Does anyone have any questions on line angle, Newman, or Fischer? Just understand that the sides are wedges, so you have to flip it, or you'll be flipping your chirality automatically, and then when you flip it after this, and it still doesn't work, then you switch your groups from left to right. Okay. Also, if you notice, your T-butyl and ethyl. Actually, I'm not sure if they will always be on the same side, but it just so happens to be on the same side here. That's something you might want to double check with your professor, or maybe in the textbook or lecture. Because sometimes I don't think they're always on the same side, like Newman projection is. Okay? And yeah, the whole I thing about dashes being on the left side, wherever that only applies to Newman projection. If you see for Fischer, we completely flipped it, but that doesn't mean the rule is automatically flipped. It just depends on, your chirality. Okay. Any questions on Newman and Fischer, or line angle, or isomers from the last whiteboard? Okay, because if not, I'm ready to take any questions you guys have. I don't have anything else for this week. Okay. Does everyone understand this? Okay, yeah, we can quickly go through another example. So I'm gonna erase this. So make sure you have everything you need. Actually, instead of erasing the whole thing, I'm going to keep the format same. Okay, all that can go. Okay. Okay. So this. So let's say we're actually looking from the other side now. Sorry, this is still carbon 3. And let's say we're looking from this side. And let's say this is that's a methyl, and this is a ethyl, and this is a hydrogen. And then let's say this is a ethyl, and this is a fluorine. Okay. So if you're looking from this side, your carbon 3 is in the front and carbon 2 is in the back. So I'm actually going to use the other way. That means it should look like this in the front and this in the back. Okay. So I'm going to quickly type in my lines because that's the easiest one. Does everyone understand where I got H and not ethyl? Okay. And then, like I said last time, my I is on the right side, so my dashes this time will also be on the right side. I believe this should work all the time, but maybe there's a problem out there that you do it, and if it doesn't work, then let me know or ask your professor. But I believe this should work all the time if you just use the I rule. And so wherever the I is, that's where the dash is, okay? All right, so because of that, I already know where to put. So on my front carbon, which is carbon 3, I have a ethyl. And on my back carbon, for my second carbon, I have, or for my dash, I have a fluorine. Okay, and then wedge, I have a methyl in the back, or sorry, a T butyl in the back, and a ethyl, or sorry, methyl front. Okay, did everyone understand where I got all of this? Newman actually becomes a lot easier once you do it. Where did the ethyl, this ethyl or this one? The line, this ethyl is right here. It's the back carbon ethyl. I extended it, or like I changed it from last time. Okay. All right. So, any questions on Newman? I think that was much easier than what we need to do for Fischer. All right. So for Fischer, let's go through chirality again, all that fun stuff. So carbon 3, okay. So let me rewrite that. So 3. All right, so carbon 3, we're going to use orange again. So so that's 1. R group is attached, or carbon attached to fluorine. That's better. Ethyl is better than methyl, and then our hydrogen is on a line. So sorry, that should be number 4. Okay, and then in purple, I'll do carbon 2. Okay, so fluorine, obviously number 1. Carbon attached to 1, 2 carbons versus carbon attached to 3 carbons. So this is number 3 actually. And this is number 4. Or sorry, this is number 3. Sorry, okay. So terp-butyl is actually now our number 2. And our R group is our number 3. And our ethyl is number 4. Okay, ethyl is also on a line, so we have to rotate both of them. Okay, so that's just a lot of extra work, but so we're going to keep our R group the same and rotate everything. So I'm going to do carbon 2 first. Okay, so fluorine's going to be on a line. ET is going to be on wedge, and then terbutyl. So TB is going to be on a dash. And then, of course, our R group. So if we do priority again, you know, fluorine, TB, R group, 3, and then 4. Okay. So if our fourth group is on a wedge, we're going to have to flip our chirality once we get it. So it looks like this is going to be R because it's going clockwise. So you always want to connect 1 to 2, and then right after 2 you should get 3. Well, that's why we're not going this way, because we have to make a whole another lap. Okay. So because of that, it's R, but because the fourth group is on a wedge, we have to flip it. Okay, hopefully that part makes sense, because these tiny details are very important, because there's a lot of tiny details in these conformations. That's why exam 1 is not my favorite. The direction we choose to rotate doesn't matter, because we'll flip one rotation, not the other. Yeah, you're right. Yeah, the direction it doesn't matter. You still be getting the same way. So like I said, it's R, but we flipped it, so it's S. Okay, so this one, carbon 2 is S, and now carbon 3, once again, we have to rotate it, so don't move the R group, and keep the stereochemistry, just move the other 3 atoms. Okay, R group, and then carbon 4, or H will be on a dash, ethyl on a wedge, and methyl on a line. Okay, so someone's confused on how I rotated it. All I did was, okay, all I'm doing is I'm rotating everything either clockwise or counterclockwise, like the other groups except the R group. Okay, the R group stays where it is, and my fluorine originally was on a dash, so I rotated clockwise. So my fluorine now went to the line, my ethyl now went to a wedge, and my T-butyl now went to a dash. Okay, so I rotated everything, or all 3 of these, clockwise. Okay, and I did this because I want to get my fourth group either on a wedge or a dash. If I went counterclockwise, I would have kept the stereochemistry, or chirality rather, and because I went clockwise, I had to flip it. But that doesn't mean our chirality is going to change depending on which direction you go, because either way you should still be getting S. Okay, so for example, let me just quickly do the other way. R, so dashes, wedge, and line. So if I went the other way, if I went counterclockwise, my fluorine would be right here, my T-butyl would be right here, and my ethyl would be right here. Okay, and if I do priority, fluorine's number 1, T-butyl number 2, ethyl, or R group number 3, ethyl number 4. Okay, so if you look this way, I go counterclockwise, I get S. My fourth group is on a dash, so I have to keep my S, and that's exactly what we got. So regardless of which way you go, you should still be getting the same answer. Just keep your R group, or like this whole other side, the same, and just rotate the other 3. Does that make sense? Okay, perfect. So now here, for carbon 3, I've switched everything. I kept my R group the same. My H is on a line. I want it to be either on a dash or a wedge. So I went clockwise. Now it's on a dash. My ethyl moved to my wedge right here. My methyl moved to a line right here. If I do priority again, I should get in orange. It should be R group 1, ethyl number 2, methyl 3, hydrogen 4. So I'm going to go counterclockwise, and I keep it because my fourth group is on a dash. So my answer or chirality for carbon 3 is also S. Okay? So I have both S's. Okay? Now, moving on to our Fischer projection, I'm going to do the easy stuff. I'm going to fill out both of these, but because carbon 3 is in the front, I believe it matters. So you have to put carbon 3 right here, and carbon 2 can go here. Okay. So carbon 3 on the plane, it's a hydrogen. On the bottom, it's an ethyl. Carbon 3, again, we're going to put it randomly for now, and then we'll do chirality, and we'll see if we have to flip it or keep it. Okay. So carbon 3, I'm just going to put ethyl on this side, ethyl on this side. Carbon 2, I'll just put fluorine on this side, and T-butyl on this side. Okay. Also, if you notice, your fluorine and ethyl for Newman projection, they're both dashes, so that should match. Your T-butyl and methyl, they're both wedges, so that should match up. Even if we didn't know which side they go, as long as they're both sticking together, that should match up. This is only for Newman projection. I'm not quite positive if that applies to Fischer also, so don't take my word for it. Okay. All right. So for carbon 3, I'm going to use orange to do priority, and we're kind of over time. So if anyone wants to leave, feel free. I'll quickly finish this and I'll end the recording. Okay. So again, to do my ranking, carbon or R group number 1, ethyl number 2, methyl 3, 4. So we are going clockwise. So I get S, but because I have to flip it, it becomes R. And do we want R? We don't want R, right? We want S. Both of these we want S. So because we automatically have to flip it because of this rule right here. All the sides are going to be wedges. Okay. Actually, I don't know what you do in a rotating scenario. Yeah. Okay. We'll just flip it in this case. And what I mean by that is just we're gonna flip these two, because when we flipped it, we got R, but we want to flip it again to stay as S. Okay. So one is like not necessarily flipping it, we're just flipping chirality, but the second time we flip it, we actually have to flip the groups. Okay. I'm sorry that if that's a little confusing. I didn't quite explain it properly. Okay. So fluorine number 2, T-butyl number 3, R group number 3, or sorry, T-butyl number 2, R group number 3, ethyl number 4. So if we do priority, we should get R, but we're flipping it, so we got S, so this should stay as S, or we don't have to like flip anything. And if you notice, this time our wedges and dashes are on different sides, and that's why I said that only applies to Newman, and Fischer it can be different. I think I did this right, but I'm also not sure because we have to rotate, so I don't know how that applies when we do Fischer. But that would be a great question for one of your professors to answer. Okay, but that's all going to be for today. Let me know if you guys have any other questions before I end. Yeah, no problem. Thanks for coming. So once again, this recording will be on YouTube or on e-learning. It should be within 24 hours. All right, I'll see you guys later.